So the first thing I'm going to go through here is the ScanExpress TPG software, which is the test pattern generation tool. This is a tool you use to actually create the test vectors, the test procedure for your board. So the first thing we do is give it a project name. I'm just going to call it ASE, and then project directory. The project directory is where you locate all your files. Now, initially, when you start a project, you're going to have to get the BSDL files for the parts that you're working with. You might have to get the memory models if you want to test memory devices, schematics, bill of materials, stuff like that. So I've already put a lot of these files in this directory, the Scan Plus Demo Board directory. So I'm going to click the Next button, and then you'll see a test flow on this left side of the screen. The green button represents where we currently are at, and the rest of the buttons is just a basic flow for actually inputting the information into the test pattern generation tool. The first piece of information that we need is a net list. So I'm going to go ahead and click on the net list. And I get a dialog box telling me, okay, I need the Scan Plus Demo Board. So I'm gonna select the Scan Plus DB net. Then I'm gonna do the same thing for the bill of materials. Now the bill of materials is an optional piece. You don't necessarily need it, but when you do have it, it gives you extra information to reduce visibility and make things more clear as to what you're looking at. So there are three pieces of information that you need. There's the part number, part description, and the reference designators. So I'm just going to select the columns for each of those: part number, part description, and the reference designator. And you can see the colors change for when each of the columns are selected. Now then there's a schematic involved. Again, this is another optional piece. You don't have to have it. But when you do, it's very useful for finding reference designators, pin numbers, net names, stuff of that sort. Once we provide all this information, we've pretty much given all the required inputs to the ScanExpress tools for test vector generation. So then we click the Next button, and it does a little bit of processing on the net list and the bill of materials. Make sure that they're in good formats and they're readable, we can understand them. And from there, then we go down the next sequence in the buttons. So now we go to the Power and Grounds button here. Power and Grounds is where we identify to the tool which of the nets are power nets and which of the nets are ground nets. Now there's an Auto Find button that allows us to do this automatically, and we can see that when I click that Auto Find button, there were certain nets that were automatically tagged as being either a ground or a power net. The information comes from the automation configuration screen, which is located in the Tools menu. So if I click the automation configuration screen, it comes up with a naming convention tab, and up at the top there's two search strings available for the ground nets and the power nets. Now there's criteria for exact name searches, and there's criteria for text contained within searches. So depending on how you modify this set of data depends on how our tool will tag certain nets as being power or ground. And this data is all customizable by the user, so you can change it to whatever nomenclature your particular board has. What came up right now is just the default data that comes with the system. Now you can sort any of these columns by just clicking them. So you can sort by the net name, you can sort by the pins per net, or you can sort on what nets are tagged as power and ground. So you can see there's a couple other nets that are also tagged as power nets that didn't show up on the screen previously because they were located down further in the net list. So once we've identified our power and grounds, now we can tell the tool what are the resistors. because there's going to be pull-up resistors, there's going to be pull-down resistors, and there's going to be series resistors. So essentially all I need to do is tell the tool what particular components are my resistors. And typically most reference designators today use the nomenclature R followed by a number. So R1, R2, etc. These are all your resistor components. So if I do an auto find here, it'll ask me for a model library. TPG has a built-in model library which you'll probably use for the majority of your projects, but in case you wanted to use your own custom library, you could. For this demonstration, I'm just going to use the basic default library. And you can see once I do that, the model column is filled in for all the resistors. And then it tells me that these are resistor components along with what type of resistor they are, whether it be a pull-up, pull-down, or series. And it knows they're pull-ups and pull-downs because we gave it the information previously on what nets were power nets and what nets were ground nets. So if I scroll down, I can see all the resistors that are tagged. There's actually one here that's not installed, that's marked as not installed. That is because this device was found in the net list, but it was not found in the bill of materials. So if you have a post-assembly bill of materials, any devices that don't show up in that BOM will be automatically assumed to be not installed on the board and therefore ignored for the test procedure process. So it makes entry of that data a lot cleaner and easier. Now down at the bottom we have resistor network components. So these aren't your standard 2-pin type resistors. These are actually network, can be isolated networks, it can be bus networks. Based on the descriptions you can see that they're bus type, 4.7K, they have a specific part number. So we can kind of infer what kind of part that is. But let's say, for instance, we didn't know what type of device this is. We can right-click on any one of these components and use the View Schematic option, and that will launch our PDF viewer and do a search for that reference designator, and it takes us right to it because it automatically creates a search macro for us. So if I zoom into that part, we can see this is RM1, and it's a 16-pin bus type resistor. Pin 16 is my common, which goes to my VCC, and the other 15 pins are my pull-up resistors. So based on that knowledge, I can go back to TPG and I can select an appropriate model for that device. So I click the resistor network button, and then I look for the appropriate model for that guy. So we know it's 16 pins, we know it's a bus type resistor network. So this is the closest match. Now if I want to dive in further, I can always use the view button to view what the pinout is for that particular part. So in this case we see pin 16 as our common and the other 15 pins are the pull-ups. So this is an appropriate model for this guy. So I select him and we can see that the model is now assigned here. And it tells us it's a pull-up, which matches what we saw in the schematic. Now there's several parts on this board that are the same part number. So this 416P-T-02-472 shows up 4 times down here. So I can select the same model for all these part numbers by just right-clicking, saying select the resistor network for all these part numbers, and then select the appropriate model. And we can see it fills in all that data automatically for all the other devices. So that's very convenient when you have a bill of materials, some of the extra capabilities that you get. And then there's one last resistor network here, which is a different part number, RN3. It is the same type of part number, but just to make sure, I'm going to use that view schematic feature again. Right click, it's going to do a search macro. It's going to find RN3. It found RN3. And we can see this one's actually a pull down as opposed to a pull up, but it's the same type of resistor pack. It's a 16-pin bust resistor pack. So I go back here, select my resistor network button, and then apply that model. And we can see he's been tagged as a pull down as opposed to a pull up, just based on how it's implemented in the schematic. So now I've tagged all my resistors, so now I'm basically done with this screen and I can move on to the next screen. So the next screen is what we call transparencies. Transparencies are like series resistors, jumpers, buffers that are enabled, that you basically pass through information from the inputs to the outputs, FETs that can be turned on, stuff of that nature. Now this particular board has a bunch of series resistors, and these series resistors have already been automatically transparented by the tool. So we recognize that series resistors are a transparented device, and the user doesn't have to do any work on his part to identify those. Now there is one component in this board that can be made a transparent device, and that's the 244 buffer. Now if I right click on that buffer and use the view schematic tool, it'll come up with my search window here, and it'll show me, okay, there's this buffer 244. It's got 8 inputs, 8 outputs, and 2 output enable pins. So when this buffer is enabled, meaning my output enable pins are activated by sending a low there, my outputs follow my inputs. So that's what we consider a transparent device. Now, knowing that information, I can go back to TPG and select an appropriate model for him. So I use the select model button, and this is the default library I was talking about earlier. I'm going to go down and select the most appropriate model for this guy. It's a buffer 244. And again, if I'm not familiar with these models, I can always view what pinout they are. So I push the view button, and it tells me the model name, tells me whether or not the model is a directional model, and it tells me what the input pins are and the output pins are if it's a directional model, or if it's a bidirectional device, it'll just say the pin numbers, or the pin numbers. Down at the bottom, it shows you pins to fix low. So it says I want to fix low pins 1 and 19 to keep this buffer enabled in order to make sure it's transparented at all times. So if I select that model, it says 240. Now buffer 244 is applied or tagged with this specific reference designator. So now this device is now considered to be a transparency and will be tested accordingly when we generate the vectors. The rest of the devices in this list are not transparent devices, so they can be ignored from this screen. A lot of these other devices are BSDL files or JTAG devices, memory devices, flash devices, which will assign a different model later on. So I click the next, and I go one step down to the BSDL files section. Now here we have a blank screen because we haven't identified any JTAG devices. Now I've already put all the BSDL files for this project into that directory I assigned earlier. So I'm just going to add, and then it lists all the BSDL files in my directory on the right here, and it shows me all the JTAG devices on the left. So essentially what I have to do is assign which BSDL file goes which JTAG device. So you can either drag and drop, or you can do it automatically using the autofind. So if I click the autofind, it'll automatically associate the BSDL files based on the file name and the part number of the device. If they closely match, then it will automatically assign a BSDL file to that device. Once everything is assigned here, if we close that screen, we can see that now I have a ScanChain that is created based on the BSDL files that I've identified to each reference designator. Okay, so I have U3 would be considered the first device in the ScanChain, U5 would be considered the last device in the ScanChain. If you needed to reorder things here, you can drag and drop things around. You can even add a tap break. So if you wanted to identify it as 2 separate ScanChains, you could. We do have hardware that supports multiple ScanChains so that you can actually tie them together externally. If you want the tool to figure out what the ScanChain is, we also have an arrange feature. So down at the bottom there's an arrange button. I click that, it'll process the netlist, it'll process the BSDL files, and it will determine what the correct ScanChain order is on its own. So you can see after I did that, it reordered everything as opposed to how I had it earlier. So it told me that U1 is the first device in the scan chain and U5 is my last device in the scan chain. And this is the correct order of this particular target. I can even show you if I go into the schematic and I show you page 1, which basically breaks down the scan chain. This is a block diagram of what our JTAG scan chain looks like. So U1 is the first device, U5 is the last device, and it just continues on from there. So what the tool found and what the board is are both matched and they're correct. So now I've identified all my boundary scan parts. The next section is to move down to the memories and clusters. So the memories and clusters are where we identify memory devices like SSRAMs, SD-RAMs, flash devices, dual port memories, stuff of that nature. And we can also identify non-boundary scan parts that we want to make sure that they're disabled so that they don't interfere with the test vectors that we generate. So the first thing I'm going to do is specify a model for my memories. So I have one SSRAM on this board and 2 SD-RAMs. So I'm going to select a model for the first one, which is the SSRAM, highlight it, select the memory, and then there's these MIF models that I've already placed in my project directory, which basically identify the pinout for each memory, how to read from that memory, how to write to that memory, how to turn it off when it's not being used, and so on and so forth. So when I select that memory, it comes up as part of the as tagged for this particular reference designator. I can double click this this MIF file and it brings it up in a text editor, so I can actually read the contents of this file and examine to see what it is exactly. And you can basically see it just identifies the address bus pin numbers, it identifies the data bus pin numbers, control bus pin numbers, how to read from the memory, how to write from the memory, how to turn the memory off after the test is completed, and how to turn the memory off when it's not being tested during other tests like the interconnect tests or non-memory related tests. So I can do the same thing for the other 2 devices. I have 2 SD-RAMs which they match as far as the part number is concerned, so I can select an appropriate MIF file for those devices as well. And just for your information, these are Corelis files. These are Corelis provided files. We actually have a directory assigned with the installation of our software that has roughly 100 of these MIF files that we've accumulated over the years for testing different memory devices. So I'm going to go ahead and select those 2, and we can see the models now applied for those devices. Now there's two more devices here which are not memory devices, but they're flashes. So the flash library is slightly different from the memory library, and that's why we have different buttons to assign models for each device. Now the flash device, so I highlight the one I want to tag, use the select flash button, and it will come up with the closest match based on the part number that was assigned to it earlier. And this comes from the bill of materials. Now if I didn't have a bill of materials, the user, in this case myself, would have to go through our extensive library of flash devices and choose the select manufacturer, and then choose the select correct part number for the manufacturer device that I'm using, and then select the appropriate package for the particular device that I'm working with. So there's a lot of information that you have available to you. You can also select different options if you wanted to program the flash or if you just wanted to read the device ID. All these options are available to you in different sections. So we have the ability to erase or not erase the part or partially erase the part, little endian, stuff like that. So I'm going to go ahead and quickly select the flash device for the second memory or second flash device that we have. This is an Intel flash, and again, the tool, based on the part number that's assigned in the bill of materials, comes up with the closest match in the flash library. So I just say OK, and then the last part here is neither a memory nor a flash, but it's a crystal oscillator. And if I right-click, I can use that View Schematic feature again. So I go ahead and search for my U14 part and zoom in here. We can see it's just a 4-pin crystal oscillator. The clock pin is the pin 3 output, and there's an output enable pin to turn this guy off. But we can see here that it's pulled high, so this clock can never be disabled. So that's kind of important for the tool to know that this clock can never be disabled. So we can assign what's called the CIF file, or cluster information file, by highlighting the device and using the disable cluster button. And then I've already placed a CIF file in my directory, and again we have a library of these devices as well, or these files as well. So I'm going to go ahead and select that one, and I can double click him and show you what the contents are. This file is very easy. It's basically telling me that pin 1 is the pin that will disable pin 3 when it's low, and then pin 3 is my output. So that's essentially the only information. Now, how the tool uses this file is it says, okay, I'm going to see if I can control pin 1. If I can drive it low, I know I can disable my clock. And that's a good thing. That means I can test the clock from a boundary scan point of view. If I can't disable this clock pin, I know that the clock is likely to be always driving, and I don't want to drive a test pattern against that clock. So that's essentially what these models, what information the model gives to the tool. So I've selected all the models for the remaining parts here. I can move on to the next screen, which is constraints. Basically, there's different levels of test coverage here: partial, moderate, complete, extensive. Partial is the least amount of test coverage, all the way up to extensive, which essentially tests everything possible using boundary scan. And then there's constraints, which if you want to fix certain things high or fix certain things low, you have the ability to do that. If you click the Add button, you'll see different constraint types: fixing things, fixing nets or pins high, fixing pins low during the test, sensing them high, toggling them. You can also manipulate the net list by merging nets together, removing pins, removing nets, renaming nets, so on and so forth. For this particular board, there's not a whole lot of constraints that I need to add because most everything is taken care of automatically. So I'm going to go to the Finish screen, which is the last screen, and it's going to give me a list of all the test steps that will be generated. So basically we can see that the infrastructure test, which is a ScanChain sanity check. There's a interconnect test, which tests the interconnectivity. Also the bus wire test tests the interconnectivity. There's a pull-up, pull-down test to do the resistors. Memory test for all the memories that we identified, and flash test for the flash parts that we identified. So when I click Finish, we go from the preparation step to the generation step. And here's a list of all the test steps that were created. Now I need to compile those to generate the test vectors. So I click this Generate All button, and it just compiles them one at a time. And if it's a successful compile, you'll see a green dot. If it's not a successful compile, you would see a red dot, and the log would give you an error message indicating what the error was, what the line number was, so on and so forth. So essentially I now have created a test procedure for that board